Good afternoon, everyone. Welcome to Free Mathcounts training, week number 6. So this week we focus on algebra. Let's look at the first problem. Okay, we have 3 variables, x, y, and z, and we got a couple of conditions, x, y, y, z, and zx. We know the products of all those variables, and we need to figure out the overall product of all the 3 variables, x, y, z, multiplied together. So when you have this kind of problem, it's kind of just very mechanical for you to think about what you have done before. Here, the 3 conditions are not kind of just arbitrary or random. They exhibit some very nice symmetry here, right? We have 3 variables, and we have every pair, x times y, y times z, and z times x. Z times x is essentially x times z. So essentially, we know the product of any pair out of 3. And the 3 conditions constitute a cyclic symmetry, meaning that if you rotate the 3 variables, x, y, y, z, zx, we got this kind of cyclic symmetry here, which is, in general, very nice. Then how do we connect the dots? How can we convert what we know to the unknown that we are trying to compute, which is x, y, z? Well, in theory, when you have 3 variables and 3 independent equations about those 3 variables, you can solve them. You can get each of them x, y, and z. But for this particular problem, there's a shortcut which really exploits the inherent cyclic symmetry property within the conditions. You have to think a little bit harder. So we try to get x, y, z. So somehow we need to at least multiply some of the already known variables together. Like if we only look at x, y, we're still missing z. So somehow you need to multiply this x, y with something that contains z, right? And you see that y, z, x, z both have z. So it will be tempting to think if you multiply x, y with y, z, what will you get? If we multiply x, y with y, z together, we got, because there are 2 copies of y, so we got x, y squared z. And this is close to what we want, but this has 1 extra y there. So if we group x, y, z together, we see there's 1 extra y we don't know yet. So still, even we know what this number is, but because we don't know y, we still cannot figure out x, y, z. But wait a second. Because of the cyclic symmetry here, you see now we have 1 extra y. If we can pair this particular y with xz, then we will get another copy of x, y, z. And we do know y, z because so far we have only used 2 available conditions. There's still 1 more, which is xz, that we have not even used yet. So that one really help us if we multiply this intermediate result x, y, z times y with the actual xz right here. Then what happens? We will get 2 copies of x, y, z, and that is x, y, z squared. So now it's very clear if we multiply all the 3 numbers together, x, y, y, z, and xz or zx, we will be able to get the square of what we want. And that really solved the problem. So because of this, x times y times yz times xz equals to xyz squared. This is really just the product of the three known numbers, 4 times 18 times 50. So this is 4 times 18 times 50, which give us 4 times 18, that should be 76, times 5, 360, and one more zero. So this is 3,600. And now you can easily see xyz should be, well, it could be either 60 or negative 60 in theory, right? But the problem already told you that they are all positive numbers. So therefore, xyz must be only positive 60. In fact, even without this condition, if you have three variables, how many ways you can figure out that whether the positive sign or negative sign, can you figure out a situation where you meet exactly the three conditions? Actually, they have to be all positive. The reasoning is not that difficult. If you have two positives, one negative, then two of them, xy, yz, and zx, should be negative, right? So if you have two positive, one negative, this won't work because we got everything positive. If you have just one positive, two negatives, again, you will get two negatives, and this will not work. If you get all three negatives, apparently, then everything will be positive. But in that case, x times y times z would be negative. But since now we are already told they are all positive, so therefore, x times y z is 60. Okay, so this is a fairly simple problem, but the takeaway is quite important. Sometimes we don't need to do the hard work, meaning that we don't have to solve x, y, z individually in order to solve the quantity being asked to solve. Because you have to read the problem carefully. The problem never asks you to solve x, y, z individually. All you need is to compute x, y, z multiplied together. So therefore, it might be a right approach if we first individually solve x, y, and z, then multiply them together, but then that may not be the quickest path. If there is an opportunity to take a shortcut, you should by all means take that shortcut. And now this is the perfect example how we can use some inherent, just a nice cyclic symmetry property to find the shortcut. Okay, this is a fairly easy problem. Wow, this problem, just like in one of the video problems, a lot of words. But don't panic, when you have a lot of words in the problem, it generally means that you just need to navigate the problem carefully to make sure that you get all the information correct and you can use the information to write down your algebraic expressions or equations. Okay, so first statement, when one integer is removed from a list of 7 integers, the mean of the remaining 6 integers is 5 less than the mean of the original 7 integers. That's a lot of words. But if you read it carefully, it's not that difficult. Okay, so you have 7 integers. You have a mean of that 7 integer, right? So you can compute that. Then if you remove one of them, there are 6 remaining, so they get a new average. But now this new average is 5 less than the original 7 integers, which basically means that you removed a fairly large number with relatively large number within the original 7, so that the average went down, meaning that the original removed number must be bigger than the original average. That's the only way you will bring the new average down, right? So this is a lot of words, but it's not that difficult to describe with mathematical expression or equations. But wait a second, just let's continue to read the problem. What is the positive inference between the mean of the original 7 integers and the integer that was removed? Okay, so you are not required to compute any of those 7 individual numbers. In particular, you don't need to compute the one that was removed. But you are asked to compute the difference between the mean of the original 7 integers and the integer that was removed. So you need to be very careful when reading what exactly is being asked for. Otherwise, you may do some actual work and even get terribly confused. So let's just model this problem with a standard way. Let's just say we represent the 7 numbers as A1, A2 to A7. Those are the 7 numbers. And assume the very first one. It doesn't matter, right? They're all just variables. Let's just assume this one is removed. So what is the original mean? We can write down as A1 plus A2 plus A7 divided by 7. If A1 is removed, we only have 6 remaining, and those are A2 plus A3 plus A7. Now the new average has to be divided by 6, right? So now we know there's a relationship between those two means, meaning that the new mean is 5 less than the original 7 means. So the equation is truly this is plus 5 equal to this guy. Okay, what do we need to calculate? Well, we need to calculate the difference, and it's a positive difference between the mean of the original 7 integers. We have already kind of correctly inferred that the one that was removed must be larger than the original average, because once it was removed, the new average went down. So this one is kind of larger than the original average. Otherwise, the new average should not go down. Should be either go up or at most stay flat if the removed one is exactly that average, the original average. So now we know A1 should be larger than this guy. And it can be actually proved by going from here, but we will not go that. We just by reasonable reasoning. So the removed number A1 should be larger than right-hand side. But since this has too many variables, it's not very convenient. And we notice that for our purpose, we just need to compute this one as a whole, right? The algebra could be a little bit clumsy if we keep working with all those 7 variables. But we also notice that for this problem, we actually do not care about individual A2, A3, A7, those 6 numbers. We can just represent it once and for all. Let's just say this is just make the algebra a little bit easier. Let's just assume the sum of those 6 variables we call that B. Okay? It doesn't change anything. It's just some simple replacement, because indeed that's all we need for this problem. We don't have anything else to say about those 6 variables other than the fact that we need to add them all together. So with that, we can rewrite the original equation as, because now A2 plus A3 all the way to A7 is B. So the left-hand side is simply B over 6. That's the new average. it's 5 less than the original average. So plus 5 equals 2. Now we can write the original average as A1 plus B, right? Remember, we just specify that A2 plus A7 all the way to A7 is B. This is not 6. This is the number B as a boy. So this is just A1 plus B. It's exactly the same thing. Now the equation looks much more easier because now we only have two variables. One is A1, the one that is removed, and B, which is sum of the other 6. Now what we need to do? We need to do A1 minus 7. This is A1 plus B. Okay, that is really interesting because here we can see that essentially we just need to evaluate this variation, the expression, but we need to find a way to connect between the two expressions. From the first one and the second one, how can we figure out what it is? Okay? Well, because in general, all the equations we have is this single equation. We cannot actually solve two variables when we have only one equation for two variables. We have a variable B here, we have a variable A1 here, but we only have one equation. We cannot really solve it. But again, we're not required to solve them individually. We just need to figure out this equation, right? So it's really how to represent this expression in terms of the information we already got from the first expression. How do we do that? Well, in general, you need to figure out it's just how to manipulate the variables or the expressions. Okay, so how do we do that? Well, in general, you can just by observing the algebraic expression. So that is what we have in the first one. Let's manipulate with this a little bit, because this is essentially you need to just think about it. If you multiply the average by 7, what will you get? Then you get the sum of A1 plus 7B. And that will give you one extra copy of the original 7. So here, if you multiply this one, would be multiply both sides by 7. This will give us, so 7 times B over 6 plus 5 equals to A1 plus B. That's the original total sum. And on this side, we will get 7 over 6B plus 35 equals to A1 plus B. But this is slightly more than 1B because you multiply 7 to a 6 number average. So you get one actual number kind of. So you can cancel out the B from this side, right side. So essentially you get 61B plus 35 equals to A1. That is interesting. So now we got an expression A1 equals to 1/6 of B plus 35. But we see that we can just plug in this into, if we plug in this right away, what will happen? Okay, so for this one, we can write this as, if we plug in A1 into 1/6 AB, then essentially we get, for this one, we can write this as 7/6 A1, right? Because there's 1/7 A1 here, minus B over 7. Okay, so if we do this, A1 plug into this is 76 times 61 B plus 35 minus B over 7. Not surprisingly, we can see that 6 sevens times 1 6, that's 71B, plus 35 times 7, that's just 30. Now you can see the magic. The magic is that after this, we cancel this out. Okay, so finally, the answer is 30. Why this is possible? Because the problem was written in a way this actually we expect this was bound to happen. We cannot solve B or A1 individually. But the expression we want to evaluate, that is A1 minus this average, A1 plus B divided by 7, must be something that can be directly derived from the condition that we were provided with, which is reduced to an equation like this. Meaning that there must be a way, otherwise this problem is intractable. There must be a way connecting what we have, which is the equation, to what we want to evaluate. Otherwise, the problem wouldn't be a valid problem. All you need is to stay cool, stay confident, and then do some algebraic manipulation. It's bound to occur. You just need to, and usually it's not that complicated. This is nothing but for you to manipulate your algebraic capability. Or of course, this is a very orthodox way of modeling the problem. We represent all the quantities exactly like the way the problem told us, right? It says that when you remove 1, new average is 5 less than the old average. That's why we wrote the equation like this. Of course, you can do some in other ways, just like how you will solve it if you don't know fraction. Okay? What will we do? Well, if you look at the standard solution from Mathcounts, they use a method that's essentially the same, but just without all the fraction. For example, if you know the sum of the 7 numbers, call that n. Now I'm using a different color just to illustrate, but if you call that n, that is sum, then if n divided by 7 is the mean, right? That's the average of mean. So therefore, n equals to 7n. In other words, you can assume the original mean of the 7 numbers is m, then the total must be 7m. Okay? So we have 2 variables, but essentially we just have 1. So 7m is the total. Now assume the one removed is x. Okay? So that means that after we remove one of the 7 numbers, our mean becomes m minus 5. That's what it says, right? This is the new mean, remember? This is the new mean. Therefore, if you times this new mean by 6, this should give you the total of the other 6 numbers. And if you plus the one that was removed, x, back, add that, this should equal to the original total, which is 7m. So this way, you just kind of choose your variable in a different way. You avoid the fraction. And then you can do the same thing. This is just kind of, it's an indirect, just a pass to the statement that was given. We don't do exact the mean. We do it in the reverse way. We choose the mean first, and then get all the the other quantities. So this is the equation you will write if you do not do what we did and use a mean as the variable. And what is the requirement here? Now you want to get the difference between the mean, which is m, and this number. So you really just want to get x minus f. Once again, we know x is larger than m. So you want to compute this one. And the basis is what you have here. So if we expand the equation, this would be 6m minus 30 plus x equals to 7m. This is admittedly much quicker because now you can see that you already get 6m, 7m right here. So if you subtract 7m from both sides or move 7m to the left, you get x minus m equals to 30 immediately. Okay, so what is the big deal here? The big deal here is that if you write the equation this way, it looks much simpler, and without all the fractions that we work with, and that way the algebra becomes considerably easier. But this is just some general belief that when you do this, you can still find the correct answer. Technically, this one is more efficient, but from a conceptual view, when you write down the equation, this one is much harder an equation to write than the original equation we wrote, because this equation is nothing but the verbatim translation of the original English, right? The problem says A, B, C. We just translate those English words into mathematical expression, algebraic expression. But here, this new equation, you need to do some kind of just indirect translation of the English. Then you can represent such translated English into some algebraic equation. The same thing, but the benefit is that at the end, the result is much more readily available. While for the earlier one, because we write the equation in some fractional way, so you have to manipulate the algebra in a little bit more complicated way. In this one, we avoid all those numbers together. We just assume m, the mean, is a variable, then translate the English statement into the equation, okay? Without ever even mentioning, except x, which is the one that was removed, we don't even mention the other 6 numbers at all. And that makes the result much more readily available, okay? So, okay, let's work on this problem. I think for this week's algebra videos, we have a lot of problems of this nature, and one of the videos specifically talk about one problem, similar problem. So what is the big deal here? Well, we have a known, that is the equation, a plus the reciprocal of a, 1 over a equal to 6. In general, we can solve a. But for those of you who have learned quadratic equation, you could recognize that this is not a linear equation because of the reciprocal term. This is actually a quadratic equation, right? If you don't believe it, let's see what that is exactly. When you have this, what is the actual equation? Because we want to get rid of a, we can assume a is not 0. So because if it's 0, then we have a huge problem. This is not well defined. So assume a is not 0, then we get a squared plus a plus 1. We multiply both sides by a. This is equal to 6a, right? And then what this means is that the true equation is this one. This is a quadratic equation. The solution because there's no way to factorize the expression on the left. A's value is quite complicated. A's, if you use the general quadratic formula, that would be 5 plus minus 25, that's b squared, minus 4ac. A is 1, a meaning the coefficient of the quadratic term, not the a here. So minus 4 times 1 times 1, that is minus 4. And this is 2. So, and a assume, I think a is assumed, no, there's no, it doesn't really matter. So, so there are two solutions for a, and it should turn out that it doesn't matter which one you choose. Eventually, if you plug in this would be the same thing. But the problem is that this is prohibitively difficult because this is not a nice radical. You have a 5 and plus a term here. So this is 5 plus or minus 21 over 2. Both are irrational numbers. So we don't want to take such an approach. Compare to the first problem that work out, those two problems can be regarded similar at a high level, meaning that we want to compute something, in this case this, but we don't want to take the hard just approach where you solve a first, then plug in into it. We try to find out whether we can take a shortcut, and that's exactly what we will do. So the observation of things like this is that you can see some strong algebraic relationship between this one and this one. And oh, this is 4. I'm sorry, 6 will be much harder. So this is 4, fourth power, not the 6th power. Actually, that makes better sense. So what is the connection between this one and this one? Well, you have already watched the video. You should know the trick, but it's worthwhile to discuss this trick, okay? When you see a fourth power term and also fourth power of the reciprocal, a structure like this is kind of symmetrical in the sense that you have A and B, but A times B equals to 1. And that's the same property here. You times A with 1 over A is the reciprocal, so you still got 1. When this happens, you always think about taking square of the original y. Why? We know the general formula, right? I'm using xy instead of a plus b to avoid confusion. We don't want to reuse a. So x plus y squared equals to x squared plus 2xy plus y squared. This is the binomial square, very important. But why this is even relevant? Because if you look at what we have, the x and the y, they are in a reciprocal relationship already. So if we do this on the original one, x times y will be 1. So one term, which is also of the second degree, meaning we are evaluating the degree of the polynomial, this one becomes a number, a constant number, which is 2, which is super nice. So if we do this, a plus 1 over a squared, this will give us a squared plus the middle one becomes a number. A times 1 over a, that's 1, coefficient 2. So this is nothing but just a 2. You get 1 over a squared. But we already know the original number is 6, so this must be 6 squared, that's 36. Why this is important? Because of the disappearance of the 2xy term, this new expression essentially gave us a squared plus 1 over a squared, right? This equals to 34. Now we see what happened. Once we know this, we can do the similar trick to go from here to a to the fourth power plus 1 over a fourth. Because conceptually, if you replace a squared with b, this will be b plus 1 over b. Now remember, a squared is b, but a to the 4th power will be b squared. So essentially, we still have a new version or new iteration of the original problem we have. How do we go from a number plus its reciprocal to get the square of that number plus the reciprocal's square? That's what we actually need to do. So essentially the same procedure, do it just one more time. Of course, the sum is different. So we take square again, what will we have? This time we will get a to the 4th power plus, remember the middle one always get cancelled out. So this is again just 2. A to the 4th power times 1 over a to the 4th power. That will be the same thing. It's here a squared times 1 over a squared over a squared. That still give you 2. So this will give you this one equals to 34 squared. Okay, so now you can see that what we want is already almost there, except that you need to subtract 2 from 34 squared. And of course, the rest is history because you have to compute what 34 squared is, which is not horribly difficult. Okay, so but the real trick is that when you have this type of problem, you don't need to go the hard way. You don't have to compute a. Instead, you can take advantage of the structure, inherent structure within the problem. You notice that this is something that you can, by squaring this more than once, perhaps, to get here from here. And that is because the binomial square, when you have a term 2xy, this will nicely become just a number if x, y are reciprocal of each other. Okay, so this is a quite standard trick, but the philosophy is not about this specific trick. It's about the general pattern. Say we want to get a particular algebraic expression, we can take the hard way to compute all the underlying numbers to get there, or we can cleverly take some shortcut. And sometimes it's even impossible to solve all the underlying variable, but we still can get the target expression, like in the previous problem. Remember, for that removing one number from 7, we could never figure out what that number is because there's no way to solve it. We only have one equation, but we have more than one variable. But still, that doesn't matter because we're not supposed to get number. We just need to get a different related expression. And the problem was written in a way you can do that. So it's really important to understand this type of problem at a high level, which is try to leverage the inherent pattern or algebraic structure within the problem to find some clever shortcut to the problem that we want to solve. Okay, so now let's look at the next problem. Okay, how many pairs of integer b and c satisfy this equation? Well, in general, for this type of problem, it's a number theory problem per se, because you need to find out what kind of just integers can satisfy this condition. But it's really about how to properly set up the algebraic expression. So it actually is this reduced to the so-called Diophantine equation, but it's really an algebraic, a new number theory problem hidden in the algebraic way. So how do we solve this problem? Well, we will have to manipulate the algebra a little bit. We don't want to get this kind of fraction, right? So we want to translate this into something without the fraction. This is c over 9. So, well, in general, we need to get rid of this one. So we multiply cross multiply. So this is b plus 4c cross. This equals to 9 times b plus 7. Okay? Now we have an equation that involves b and c. So we only have one equation, but we do know that the b and the c are integers. So integers, but it didn't say positive integers. So we have to be careful, okay? So why don't we write down this? So this is essentially bc plus 4c equals to 9b plus 63. So bc plus 4c minus 9b minus 63 equals to 0. So how do we solve this problem? Well, there's something called, in the ALPS book, they call Simon's favorite factoring trick. But there's a general pattern about this. When you have an equation like this, you have two integer variables, b and c, right? You have their product. You have each individual b and c with different coefficient. You have a constant term. This can always be factorized in a way that gives you a multiplicative relationship. What does that mean? So essentially we are discussing that so-called Simon's favorite factor trick. Look, you have a degree 2 term, meaning that you have b times c multiplied together. This is what we call degree 2, because now you have two variables multiplied together. You have both linear terms. You have a c term, of course it has a coefficient. You have a b term, has another coefficient, and you have a constant. With this, you can always write the left hand in a way like a b plus something times c plus something, then equals to some number, integer here. Why is that? Because you can see that what happened on the left hand side if we multiply this out. Of course, each question mark could represent a different number. We didn't mean all the three question marks here are exactly the same number. So it's there BC, we already have that, plus some number times C, plus some number times B, plus some those two question marks multiplied together, and equals to another question mark. All the question marks could be different, but you do see that how this matches up. It has to, right? When you have something like b plus an integer times c plus an integer, you always get an expression like this. But you already have all those ingredients in the original equation that we have. Look, BC matches BC here. That's the fundamental thing. And we do have some C term. So now we know this guy matches this 4C, and this quotient B minus matches this negative 9 times B, or subtracting 9B. And we don't know whether this one matches with this one, but it's okay because now the right hand side is not limited to 0. We don't have to match this 0. So we have some freedom to choose any number. So instead of matching this 63, we can just do whatever we can have to get a new number on the right hand side. So if that's the case, you will see that this question mark times C, which came from this question mark, must be this number 4. So therefore, you can easily write the guessed expression as B plus 4, because this 4 will times C terms here to match the 4C you have. Similarly, For the c term, this must be subtracting 9, because this way, subtracting 9 times b, you will get subtracting 9b or plus negative 9b in the original one. So we immediately, from the coefficient of the c term and the b term, and assuming it's bc which has no coefficient. If bc does have a coefficient in the original equation, let's just say if this is 3bc, then we have to do a little bit extra. We have to divide both sides by this coefficient. We call normalization, meaning that we always want the highest degree term, which is bc term, has a coefficient 1. If it's not 1, we force it to be 1. We can always divide the equation by that coefficient. Of course, that will change the other coefficient and the constant number, but we don't care. We really don't care. But once you do that, you can always write down your expression in such a way so you get b plus 4 times c minus 9. But remember, we cannot perfectly match the negative 63 here, but that's okay because we still have another number to write on the right hand side of the new equation. Therefore, this must be, we know BC matches BC, 4C matches 4C, negative 9B matches 9B, but here is just negative 36, right? 4 times that. But originally it has negative 63, so we have to subtract another 27 here to be exactly the same as the original equation. So in that case, the right hand side would be 0. So meaning that the original equation now on the left hand side is this one minus 27, and we can move it to the right hand side to get 27. Okay, this is the so-called Simon's favorite factoring trick. The gist of this trick is that once you have a Diophantine equation, we call that Diophantine equation because it's just if we are not limited to find the integer solution, the equation is not solvable because we have two variables and we only have one equation. But we are limited, constrained to only find the integer solutions. So there's a lot of trick we can do. And the trick here is that once you have this type of Diophantine equation, you have two variables. You have the second degree term, which is the two variables multiplied together. You have all the first degree linear term, b and c, and some constant numbers. We don't care. If it doesn't have, if it's not there, then it's 0. We really don't care. So the gist is that we have those three things. We have degree 2 term and a degree 1 term, which is just for the two variable. Then we can always factorize this thing. Whatever integers we have here, we can always factorize this into something like this. It's just each variable plus an integer, and they multiply together, and we can actually directly figure out what those integers are based on the coefficient you see here. And there's always some residual integer remaining. It could be 0, but usually it's not 0. If it's 0, then we really have a very easy problem to solve, but usually it's not 0. So in this case, it's 27. Why this is important? Once you are here, you can see the nature of the problem. The nature of the problem is that we need to find integer solutions, right? So b and c must be integers. Therefore, b plus 4 and c minus 9 must remain integers. Integer plus or minus integer, still integer, can be negative, but that's still integer. So two integers get to 27. So this really becomes a factorization problem because you can only have a quite limited way to factorize 27. How many ways you can factorize 27 into the product of two integers? First, without considering negative numbers, it can only be 1 times 27 or 3 times 9. That's it. 27 is 3 cubed. That's the only way you can factorize this. Okay? So you have two pairs, but you have to be very careful. Alright? So because it didn't say all those integers are positive or negative, so all negative things are allowed. So you have to consider more pairs, like a -1, -27, -3 times -9. Okay? If that's the case, you just see that there are essentially 8 ways. Why 8 ways? We originally started with 2, but remember the factorization didn't say B or C correspond to this. So you can swap those 4 pairs to get another set of 4 pairs. So 127, that's 27 1, right? And 3 9 is 9 3. And similarly, you get in total, you will actually have 8 pairs. This is a critical point. If you do not recognize this fact and not very careful, you may not find all the solutions. This really exhausts all the potential pairs. Any potential pair, because in this case, because you are trying to solve B and C separately, the order between your two factors actually matters. So 127, you will also get 27 1. Now you get all the possible ordered pair to factorize 27. And all you need is to check when 24 equals to each of those 8 numbers. At that time, simultaneously, C minus 9 must be the corresponding number on the right-hand side. For example, if B plus 4 is -3, then C minus 9 must be -9, right? Because they multiply together to get 27. So this is one of the 8 solutions, and this gives you, of course, B equals to -7, and C equals to, wow, C is 0. Nice, but it happens. So in this case, this is one solution. So you repeat this for all those pairs to get 8 pairs of solutions. You can write a table, but do whatever you want. Just make sure that you recognize that although the numbers are fairly simple, you still get quite a large number of pairs. You got 8 pairs, not 2, not 4. You have 8 pairs. You have considered the order between the factors. You have considered both negative case and positive case. Therefore, with all the variations, even 2 possible factorization, 1 times 27, 3 times 9, will actually give you 8 pairs of equations. And of course, each pair is different from the other 7, so you get 8 sets of solutions. So this problem is quite interesting and very representative because once again we learned the Simon's factoring trick. Okay, and this trick will appear again and again in AMC 8 or Mathcounts. Quite a routine trick. Okay. Next problem. Well, this one is a little bit harder, right? Really? Not so. It looks a little bit familiar. We already solved a problem like this if we are evaluating a to the 4th power plus 1 over a to the 4th power. In that case, all the even numbers is, right? 2, actually not even numbers, just 2 to the power, 2 to our exponents. We can get a square, we can get the 4th power, we can get the 8th power. All we need is to keep squaring the previous step. the middle term always gets cancelled into an constant integer. But what if we have a cube here? Should we panic? There's no way by squaring a plus 1 over a to get a cube, right? Wait a second. I think we can still factorize this one. Remember the factorization formula. What is a cubed plus b cubed? Here's, maybe I should write it in x and y, because we are already using a to avoid any potential confusion. So what is x cubed plus y cubed? This is x plus y times x squared minus xy plus y squared. So now, with the understanding of the trick in the previous problem, we already know this. But we don't know this yet, right? How can we solve this problem? If you really need to think about this, you should recognize that essentially we will still do some trick so that we can reuse the fact that we know x plus y. In this case, is a plus 1 over a. Why this is true? We already know this. So a cubed plus 1 over a cubed equals to a plus 1a times x squared, which is a squared. Now we see what happened. The very reason earlier we can compute something like a squared over 1 over plus 1 over a squared is because the original midterm is 2 times a times 1 over a. This one got cancelled out because the two are reciprocal. A and 1 over a, that's reciprocal. So they got cancelled out. But in this expression, this already got cancelled out for us, right? That's super nice because although we cannot directly squaring what we have, the factorization still gives us something very close because this midterm is just minus 1. Now you see the trick. This is nothing new. We already know this. We know how to do this because at that time we subtract 2 from in the middle. Originally, remember, the original midterm is plus 2. We get this by subtracting 2 from the square. Now, all we need is just subtracting 1 more, right? So, in order to get this, it's just nothing but subtracting 1 more from what we could compute. So, in other words, this is nothing but a plus 1 over a square subtracting 3. Don't you see it? That's how you compute this problem. Okay, so it's still fairly the same trick, except that don't get panicking. Don't become really frustrated because you cannot. Math is never about memorizing the trick and blindly use that trick. You have to be open-minded. You have to understand the fundamental nature of the trick, not the trick itself, but the true idea behind the trick, so that if the problem somehow changes a little bit, you don't have to blindly apply the trick. You can, based on the same idea, to adapt to a new trick. And in this case, it's nothing but subtracting 1 more. And then multiply this number with this number to get the cube one. Okay? So essentially the same problem. Our time is up, but I want to discuss one more problem, which is relatively a little bit more difficult, but still shows the central topic of the day. That is that when you manipulate algebra, the problems usually are ready for you to take some shortcut. At a high level, this is the same problem. You know some conditions. You know two conditions, x plus 1 over y, y plus 1 over z. But you have three variables, right? X, y, and z. You have three of them. So for this problem, you cannot even solve exactly what x, y, z are because you only have two equations. You need three independent equations about x, y, z in order to solve all of them. With only two equations, that's impossible to do. But you're not supposed to get x, y, z individually. All you need is to get x, y, z. So what is the closest problem that we have worked on so far? It's the very first one. Remember, we got xy, yz, and zx, which is essentially xz. We got those three. We can manipulate them to get xyz. And the manipulation in that case is very simple. We just multiply the three all together, get the square of the right-hand side, so take the square root. That's it. So that is the easiest trick. But this time, we get x plus y, 1 over y. We get y plus 1 over z, right? We don't even have a third one. In this case, we would expect that we get something like z over 1 over x. We don't even have this one. But is that really relevant for us to solve this problem? The answer is no. Because those two are all that we need in order to derive xyz. But fundamentally, the same idea. We need to somehow figure out a way to manipulate those two equations to lead us to solve this problem. It must be doable because this is an artificially made problem. It's not a real problem from a real world. This is a man-written problem to challenge you. There must be a way to get there. So you should not lose that confidence. Instead, you should be 110% sure this is completely doable. It's just that the underlying algebra may be a little bit more complicated than you want to. First of all, both equations only involve two variables. You need the third one, right? So the only way to get all three variables into the same algebraic expression is to somehow combine them. And naturally, when you have this type of thing, 1 over y, the reciprocal, you don't want to add them. You can add them, say x plus y plus z, but that intuitively doesn't sound right because you want to get x, y, z in the multiplicative relationship. You want to multiply all the three together. So very naturally, you want to give a try. What happens if you multiply both left-hand sides? And it doesn't take long for you to recognize when you do that, there is as one term, because 2 terms times 2 terms, you will get 4 terms in total, but at least you see something really nice. You have 1 over y, and you have y in the other one. So when they multiply together, at least this particular one will get cancelled into a number integer. So let's just do that to see what happens, okay? This is just a well-educated guess. This does not get too much justification other than the fact that we want all the three appearing together in the multiplication relationship. For that reason, we really want to multiply the two. So if we multiply the left-hand side, we get xy, 1 over y times y, that's 1. Now we got the z term. This is x over z and plus y, 1 over yz. Okay, right-hand side, surprisingly nice, it's just 1. 2 and 1/2, right? Okay, what is this? Well, we don't like the fractional bottom here. We always want to use an equation that does not show any fraction. So we multiply both sides with yz. So this becomes xy times yz. So it's y squared z. Well, we saw this before, earlier, right? This plus yz plus times yz. So z get cancelled out, plus xy plus 1. But remember, the right-hand side, that's a yz. This came from the fact that we have 1 here, so we should have canceled that earlier, but it doesn't matter. We cancel that now. So this is a new equation. The equation is obtained by essentially multiplying both sides together. So this is xy squared z plus xy plus 1 equals to 0. What is this? If you think about it, you will not be surprised that this is actually quite close to what we want to do. Again, why is that? Because now this time you get something like this. You want to get xyz, right? The closest to this one is this number. But if we really want to get this one, we have to divide this guy by a y, right? And let's see what happens if we do that, so that we can force us to generate xyz term. So now we do, which also means that when we do it earlier, we could just multiply z to get xyz here. So essentially, we are reversing ourselves halfway. We multiply both sides by yz. Now we recognize now we need to further divide it by y. So that means that we should only multiply both sides here by z in the first place. But it's not too late. So we get xyz. When divided by y, this becomes x. And when divided by y, this becomes y over y. 1 over y. Not y over 1. 1 over y. Hey, wait a second. This guy is right here. So this problem is much easier than it looks like. All we need, in summary, is just multiply the two sides together, get this one. At that point, we can cancel out y, the constant, because we already see when you multiply y with 1 over y, you get 1, but originally there is 1, so we cancel that. And for this one, you just multiply both sides by z, not yz. When you multiply this by z, you get xyz plus z cancel out plus x, this plus 1 over y. And this one is already given to you. This is 2. Therefore, xyz is nothing but negative 2. This is so actually simple, right? Why? Of course, because the problem was written in a way that you can get this easily. This is just Mathcounts or AMCA. You're not supposed to spend half an hour to solve a problem. That's why Mathcounts and AMCA are actually quite easy math competitions. Or at least the problems are not super difficult. You're only supposed to solve each problem in a couple of minutes, maybe 5 at most. Otherwise, you will not have time to do anything else. So don't be scared by the seemingly complicated algebra in the problem. While they look complicated, if you just have patience and the courage to do a little bit of manipulation, the problem will become much more apparently solvable. It just simply represents itself. Don't you agree? We just get this right here. So this is nothing but just to do multiplication together. You should have that confidence. Anything more difficult than that usually will not be a Mathcounts problem, or unless you go to math count natural or state, usually there are a few common problems at the very end of the sprint or a team round. To have this kind of really, you need to spend a lot of time, like 15 minutes. But in general, nobody can solve those problems anyway. So I guarantee you that nobody ever get a perfect score. I believe in the say just team run, no, just individual run sprint at a national level. There's always one or two difficult problems which takes a lot of time. They intentionally wrote those problems. But for a problem like this, truly, it takes maybe 2 minutes at the most if you are good at algebra, and you should never lose this confidence. Okay, that's it for this week. I will see you on Sunday. Bye.